Okay, physics, free fall. So free fall is a sort of a special case of, or a common example of uniform acceleration, and I want to talk you through some of the implications of that so that you get it around your head. Here's the challenge, right? So I have somebody who's going to throw a ball. It's going to throw it straight up. As soon as I let go of the ball, it's in free fall, right? It doesn't matter the direction it's going, right? As soon as I let go of it, it's in free fall. So once I let go of it, the only sort of force it's experiencing is gravity pulling it down. So we're going to ignore air resistance. Later on, we'll get into drag, and it'll be specifically clear where you do have to worry about air resistance. But for right now, we're going to assume that there is no drag. So I throw something in the air, I let go of it, it's going to experience. So what do we mean by this? So I'm going to draw three graphs, right? So I'm going to have a graph that represents acceleration over time, right? My acceleration is going to be only coming from gravity, and I'm going to decide this direction is going to be negative and this direction is going to be positive. You get to pick. So I'm going to decide by convention. Usually we have downwards being negative, but you get to decide. Sometimes it's more convenient to have upwards be negative. So what is my acceleration? My acceleration is going to be negative, right? So this is going to be negative 9.81 meters per second squared. That's the force of gravity. It happens or it's the acceleration due to gravity. It's really common, so we're going to give it a value of g. The value for g is 9.81 meters per second squared. Notice this isn't negative, right? And a really common mistake is to add in too many negative signs, right? So be careful about it. So I'm going to give you a value for g. This will be provided for you on this formula sheet. It's going to have this value of 9.8. And you get to decide, is that going to be positive or negative? You need to know it's pointed directly towards the center of the Earth. Okay, so that's acceleration. What does velocity look like? So as soon as I release this ball, well, what does my velocity look like? So let me draw a velocity graph, right? So I'm going to have velocity over time. What's going to happen is it's going to start going up in this positive direction. So it's going to start with positive velocity. It's going to come to a stop. It's going to have zero velocity. And then eventually it's going to be going fast on the way back down. And my ruler. And because acceleration is constant, that means I need to have a single straight line. Imagine all those dots are on the same line. So I have a single straight line for velocity. Right? So notice, acceleration is the rate of change of velocity. So the slope of my velocity graph is going to be acceleration. If my acceleration is the same everywhere, that means my slope needs to be the same everywhere. Really common to want to put, going like this. No, don't do that. Right? My velocity starts positive, goes to zero steadily, and then steadily becomes negative. Okay, if we're to make a displacement graph, over time, explain to yourself why I didn't start it at zero. Right? So what's going to happen? Well, I have negative acceleration. So when I have negative acceleration, I'm going to have a frown. So on my displacement graph, so I'm going to make it go like this. Notice my velocity is going to be the slope here. The slope of the tangent line starts out positive. My slope goes to zero. Oh, look, it almost lines up. And then finally, my slope is going to be negative. So free fall. So this is what it should look like for displacement, velocity, acceleration graphs for something that's in free fall. A couple of handy things to remember about free fall. So there are some things. So if I'm going up and back down to the same spot, right? So I'm going to stop here. So if I'm going up and back down to the same spot, the amount of time it takes to get to the peak is 1/2 the total time. That's really handy and it's helpful sometimes, especially when we get into things that are in free fall and we want to figure out how long it's going to take. You can just calculate how long it's going to take to get to the top and then double it. And that's how long it's going to take to get back down. Second thing, so if I'm going in and I'm going to catch it again, so the velocity that I throw it up with, when it gets back to my hand, is going to have that same magnitude of velocity just in the opposite direction. Right? So let me list these out. Three really important things. So one, acceleration is going to be constant always throughout. So acceleration is going to be g. You get to decide what's positive or negative, but acceleration is going to be the same throughout. 2, right? If I'm coming back down to the same level, the time to peak is going to equal 1/2 the total time. I don't know. I hope you can read that. Who knows? And the last thing is velocity. So if I'm coming back down to the same level, the velocity up. So just my vertical velocity, right? My velocity up is going to equal the magnitude. So this is how we're going to do this. So if I put lines on either side, right? So absolute value. So the magnitude of velocity going up is going to be equal to the magnitude of velocity coming down. Right? So the absolute value of velocity going up is equal to the absolute value of velocity going down. Fourth thing that we're going to get into a little bit later as we get into hurling things off of cliffs, that only the vertical dimension is going to be affected by gravity. The horizontal dimension is not affected by gravity. We're going to get into that in more detail. But just to remind you, if you haven't seen this before, only vertical velocity is going to be affected by gravity. Okay, hope that helps. We'll talk to you soon. Bye.